Presented by Caltech.
So as you can see here, there's a couple of déjà vus that you probably ran across campus this week, because we are having the Global Methane Workshop, basically a Linde Center sponsored workshop this week, where Daniel Jacob will be around the whole week almost basically. But today he was willing to actually give this more or less big lecture on the Wednesday for the ESE seminar. And Daniel is the Vasco McCoy Family Professor of Atmospheric Chemistry and Environmental Engineering at Harvard University. And you will recognize him here and over there. We were thinking of doing the infinite loop here, but that doesn't really work out. And even though the name doesn't really suggest it, he did his bachelor in Paris at in chemical engineering at the École Supérieure de Physique et Chimie, if I pronounce this correctly. And then, for those who don't know, he actually did his PhD right here at Caltech. And after his PhD, he moved to Harvard as a postdoc. It just took him 2 years, I think, according to the dates that I have, to actually get elevated to the tenure-track faculty, where he was promoted to the full professor in relatively short order thereafter. And it's really embarrassing to cite these statistics, because he authored more than 300 papers, and his H-index is somewhere above 130. So he's really one of the prominent people in this field, and it's a pleasure to have him here. But if you want to move one slide further, since he spent some time here at Caltech, and it was kind of in the 80s, I asked Mike Hoffman, who basically worked with him, to say a few words about his time here at Caltech before he starts his talk.
Well, Danielle was one of my first PhD students here at Caltech. I've been at the University of Minnesota before, and I had PhD students there, but Danielle is my pride and joy in terms of my academic career, and his productivity over time. Truly amazing. But he was a wild and crazy guy when he came to Caltech. He actually came here to avoid French military service. Well,
I did my military service here.
yes, that's what I mean. So he intended really only to get a master's degree, but he got turned on during the first year in terms of the academic environment and the Southern California sunshine and the ambiance and everything else I won't mention. But you can see he was an experimentalist as a graduate student. Did a little bit of modeling towards his final year of his PhD studies, and that took him forward to his present-day career. So that little beginning in modeling became his entire career. And he is one of the world's leaders in global atmospheric chemistry modeling, if not the world leader. John, of course. Okay, it's all yours.
Yeah, stop while you're ahead. Hey, thank you very much, Mike. Thank you, Christian, for this warm welcome. You can't imagine how happy I am to be back at Caltech. It's always so wonderful. Not that I'm not happy at Harvard. You know, I like to say there are 3 great things about Harvard: June, July, and August. But that's not really true, because I've been there 33 years, and there's good reason for this. But I'm very lucky to be able to come back here with some regularity and see many old friends and meet new ones. And this time in particular is a particularly great opportunity, because we have a methane workshop that has been organized by Christian Frankenberg and Eric Court, and brings together a number of distinguished colleagues to try to understand the factors controlling atmospheric methane. So it's been a very intense week, and it is fitting that I should tell you this afternoon about what is it that we know about what controls atmospheric methane. So start off with a little movie. Everybody likes movies. This is an oil well in the Netherlands, and it's courtesy of my student Bram Massacres. The problem with trying to understand methane sources is that It comes from all kinds of little leaks from all kinds of processes. And well, we'll be talking about this over this coming hour. First of all, what is it that we care about methane? Well, methane is the second anthropogenic greenhouse gas after CO2. On the basis of ice core records, we know that the concentration has, increased by a factor of 2.5 since pre-industrial times. And methane is a greenhouse gas, meaning that it absorbs in the thermal infrared range of radiation emitted by the Earth's surface as a black body. And it is largely transparent to solar radiation. So in this little diagram, if we consider the Earth at radiative equilibrium between the energy coming in from the sun and the black body energy being emitted in the infrared, so climate equilibrium will be defined by the equality between these two fluxes. If I add some greenhouse gas, such as methane, I will hinder the escape of infrared radiation. I will send some back to the surface. As a result, I will have an imbalance between the flux in and the flux out. This imbalance is called the radiative forcing, and it will eventually lead to a warming of the Earth as it tries to relax to a new equilibrium. This radiative forcing is a standard currency used for climate policy and also by climate scientists. It's a quantity that's fairly easy to compute, is fairly robust, and allows us to compare the importance of different climate forcing agents. So this is from the latest IPCC, and it shows the radiative forcing since pre-industrial times contributed by different long-lived greenhouse gases. So you see my point about methane being the little brother of CO2, being the second anthropogenic greenhouse gas. But some of you may not appreciate that methane is actually not that small compared to CO2. And there's a reason for this, has to do with atmospheric chemistry. So methane, as the most reduced state of carbon, gets oxidized in the atmosphere. And as it's oxidized in the atmosphere, it produces ozone. As you know, ozone near the surface is a major air pollutant, but ozone in the middle upper troposphere is a very powerful greenhouse gas. And so when we're looking at the radiative forcing from methane emissions, we have to account not only for the methane, but also for the ozone that's produced from that methane. But it doesn't stop there. The oxidation of methane will eventually produce water vapor, and some of the methane goes into the stratosphere and enhances water vapor there. And water vapor in the lower stratosphere has an extremely powerful greenhouse forcing, and this is what you see in blue. And finally, when you oxidize methane all the way, you get to CO2, and CO2, of course, has an additional radiative forcing. So if you add up all these four effects, you get a radiative forcing from methane that's about 60% that of CO2. All right, what does that mean? What that means is that the warming that we have experienced so far, say over the past century, is due to methane, about 60% the contribution of CO2. In other words, 60%, methane contributes 60% as much as CO2 to the warming that we have experienced in the past. A really, really big deal. Now, it gets a little bit more complicated when we try to say, well, what does this mean in terms of climate policy, in terms of controlling future emissions? Because the lifetimes of methane and CO2 are drastically different. Again, methane gets oxidized in the atmosphere, and its lifetime, we know it very well, is 9 years. On the other hand, the lifetime of CO2, well, it's complicated, but the effective lifetime is more than 100 years. What that means is that methane is really most relevant as a near-term climate forcer. If I control methane emissions today, I'm going to buy myself a cool decade or two. And then I'll be back to where I started, because the methane will have totally gone away. Okay? If I control CO2 today, I'm buying myself a cooler Earth for a century or more. So this is very, very different. So methane and CO2 emissions should not be viewed as equivalent in climate policy, even though they are, of course. And the regulatory agencies, report methane in terms of CO2 equivalents. That's awful, because they're not at all the same. This is an important point because many scientists think that methane is a distraction, and that by going after methane emissions, we're getting our balls off the real issue, which is to go after CO2. Okay, and indeed, fair enough, because some countries are actually using controls of methane as a way to, whoops, cute kid. Let's see. Okay, well, I think I totally lost my connection here. Hmm?
Superman is on the way.
Okay.
That's your desktop, right?
Huh?
That is your desktop.
Yes, that is my desktop. Okay, well, I'll keep on talking. So,
Just pull it again.
yeah, okay. So, so as I was saying, methane can be viewed as a distraction because you control methane emissions, you are affecting climate only over a limited time window. On the other hand, climate change is not some theoretical construct about the next century or so. We're not just thinking about the Earth we're going to leave to our great-great-great-grandchildren. Climate change is happening right now. And if we're concerned about what's happening with the Arctic sea ice, if we're concerned about sea level rise, well, we got to take short-term measures as well as long-term ones. So what that means is that methane should be viewed as part of our climate policy portfolio, but for reasons totally different than CO2. It's operating over short-term horizons. CO2 is operating over longer-term horizons. We care about both, and we can have political debates about which one is most important. I call methane kind of a self-indulgent greenhouse gas, because if we go after methane emissions, we're benefiting ourselves, never mind the great-grandchildren. But basically, we got to appreciate this. Those are two very different timescales. Okay, the other thing is that reducing methane emissions has some side advantages. It has air quality co-benefits. Again, methane makes ozone. Ozone is a nasty air pollutant. You control methane emissions, you're going to decrease ozone. And finally, methane is a valuable fuel. And this is a point that we'll go back again. When we emit methane to the atmosphere, it's inadvertent. It's through leaks. It's not by design. You say, whoops, we emitted methane. Whereas when we emit CO2 to the atmosphere, it's totally by design. That's the whole idea. You take hydrocarbon, you burn them, you make CO2. In the case of methane, instead of emitting to the atmosphere, you'd much rather trap it and burn it and get some energy out of it. So there is some additional economic reason to try to go after methane. All right. So as I was saying, methane mainly comes from leaks. So basically, it's often a very small terms in the overall output from a given activity. There are three types of methane sources. There's a biogenic source in which methane is produced by microbes under anaerobic conditions, conditions deprived of oxygen. There's the thermogenic source, in which methane is produced in the solid earth from dead organic matter under very high conditions of pressure and temperature. And then there's a pyrogenic methane that is produced as a small yield from combustion. Biogenic sources include the largest natural source from wetlands. It also includes rice agriculture, which is basically artificial wetlands. Livestock, or another type of biogenic source. Landfills, wastewater treatment plants also are biogenic sources. Then we have the thermogenic sources, so we have oil production. Anytime you extract oil from the ground, there's natural gas that comes with it. Natural gas is mainly methane. There's natural gas at all stages of the production to the distribution chain. And then there's venting of coal mines. Coal mines contain a lot of methane and has been responsible for scores of accidents over the history of exploitation of coal. And you want to vent that methane, or ideally you would want to use it as fuel. And then we have here the pyrogenic methane associated with fires, and we heard earlier from Jim Anderson in workshop about that source. Okay, so interestingly, we know what the global source of methane to the atmosphere is. And we know it very well, within about 10%. And the reason for this is we know the lifetime of methane in the atmosphere against oxidation by the OH radical and other very minor sink processes. I don't want to go into the details of this, but we know that the lifetime is 9 years plus or minus 10%. And so by mass balance, if we know how much methane there is in the atmosphere, and we do, we can deduce what the source has to be. And from that, we get a total source of methane of 550 teragrams per year, plus or minus 10%. Okay, so we know the size of a total pie. But now slicing it is a much bigger problem. What I'm showing you here is the partitioning between sources from the Edgar inventory that's widely used in the research community, and then the so-called LPJ wetlands inventory. So individual sources, and we heard about this from Philippe Bousquet at the workshop, are uncertain about a factor of 2. So the cutting of this pie is uncertain by a factor of 2, and that's where the global sources, the sources on a regional scale, are even more uncertain. You shouldn't be surprised by this uncertainty because, again, methane comes from leaks. It's a small residual of activities, so the emission factors associated with individual activities are very, very difficult to establish. Now, methane has done something, again, that's really weird over the past 40 years, and the panel on the right must have been shown at every talk at this workshop we've been having this week. It's the fits and starts of methane over the past 40 years. When you look at the evolution of CO2 since the record started in 1958, those are now real atmospheric data, and this is from the NOAA compilation. What you see is basically what you would expect, some kind of exponential increase associated with increased fossil fuel combustion. Okay, fine. Now, what about methane? Now, when I was at Caltech in the early 80s, methane was increasing at about 1% per year. And this is when we were just starting to care about it. And then something funny happened in the 1990s. It started to level off. And then in the 2000s, it was actually flat. There were a few years where it was actually decreasing. Oh, there was a flurry of papers explaining this leveling off of methane. It was due to Pinatubo. It was due to the demise of the Soviet Union. It was due to change in rice practices, all kind of thing. Then it started to increase again. In 2006, we started to have a so-called renewed uptick, or renewed, I don't know, renewed growth in the past decades. And this growth has been sustaining itself now for a decade. And again, there's been a flurry of papers trying to explain where this could be coming from. And explanations include oil and gas, of course, in particular fracking, livestock, the growth in tropical livestock as feeding habits change and population grows, changes in wetlands, perhaps feedbacks from climate change, changes in the sink, OH, and I'll talk a little bit more about this later on. But, you know, before we get too excited about trying to interpret what this uptick is coming from, I think what's important to realize is that this whole uptick over the past decade represents only a 3% change in the sources, or maybe the sink, if that's the case of OH. So we're spending all this literature, we're spending all that effort trying to understand a 3% change when we have no idea where the 2.5 baseline increase in methane since pre-industrial times is coming from. Okay, now this is not to dismiss efforts to try to understand the uptick over the past decade, because, as you know, when you have a change in the slope like this, that provides you with information. And maybe that information can provide you with a clue to try to identify the sources important for methane. But we have to put it in perspective. And a particular reason why I want to put this in perspective is there was a feeling, you know, when methane was leveling off in the 1990s, 2000, people say, oh, whew, we're done with methane. It's leveling off. It's leveling off. We're done. Well, yeah, it's leveling off at levels 2.5 times what it should be. So another way of looking at this, which is that if somehow we managed to decrease methane emissions by, say, 5 or 10%, we would see methane going down. If we saw methane going down and we could relate this to some measures that we had taken for climate change mitigation purposes, that would be wonderful in terms of accountability of climate policy, saying, hey, we can do it. And then that could hopefully provide some motivation for doing that for CO2 as well. Okay, now, I talked about the uncertainties in methane emissions. The whole purpose of this workshop was to try to figure out how can we better understand those emissions. So, how do we do this? Well, we start from emission inventories, what we call our bottom-up knowledge of methane emissions. Now, emission inventories take the activity rates, so for example, the number of heads of cattle, times the emission factors, so for example, the amount of methane emitted per head of cattle, and then come up with estimates of the associated methane emissions. The activity rates typically come from socioeconomic data or from some other geographic information. The emission factors may come from theory, or they may come from experiments, our understanding of processes. The point is that those bottom-up emission inventories provide us with a fundamental knowledge of how much methane is emitted and also where it's coming from and how it is being emitted. But as we have seen, those inventories can have large errors. So, how do we go about trying to address those errors? One way that we can do this is through atmospheric observations. Now, we can measure methane in the atmosphere from a range of platforms. We can do it from surface sites, and NOAA has a network that goes from pole to pole. There's a TCON network that Deborah Wunsch told us about that was developed by Paul Wenberg, that has been a huge success, that measures the methane column from a network of sites. We have various aircraft campaigns. We have routine aircraft profiles done by NOAA, and Colm Sweeney told us about this. And then we have satellites, okay? And I'm going to be spending a lot of time talking about satellites because this is the kind of stuff that I do. But from a general perspective, how do we use those observations to improve our understanding of emissions? What we observe are atmospheric concentrations. What we want to get at are emissions. So how do we go from one to the other? The way to do it is to have an emission inventory, such as this one, that's the Elgar plus LPJ inventory, that has relatively high spatial resolution. Okay, because with this inventory, combined with an atmospheric transport model, we can come up with a prediction of what the atmospheric concentrations should be. Okay, we come up with a prediction of these concentrations, and then we confront this to observations. And we then try to interpret the mismatch in terms of errors in emissions. And the way we do this is through a technique that's called inversion. And it's called inversion because the forward model, the transport model goes from emissions to concentration. Here you go from concentrations to emissions. But in fact, it's really a statistical fit to the observations on the basis of everything that you know about the system and your best characterization of the errors. Because as you may expect, there's errors involved in all components of this scheme. Okay, and I will tell you a little bit more about those inversions of emissions in just a little bit, in just a little while. So, as I tell you, I deal with satellite observations, and remote sensing of methane can be really easy. really, really, really easy. All right, this is the Aliso Canyon methane leaks. This is a slide I got from EDF. This is, this is, of course, an infrared camera, right? So you're seeing methane in black because it absorbs in the thermal infrared. Okay, oftentimes the sources are not so kind, and you have to do a lot more hard work to try to quantify them. Now, In fact, the thermal infrared, where from which you get this movie, is not the best part of the spectrum to observe methane, because in order to detect methane in that wavelength range, you need to have a thermal contrast with the surface. A much better way of observing methane in a way that's sensitive down to the surface, because you really want to be sensitive down to the surface in order to get information on the emissions, is through the technique that we call solar backscatter. Solar backscatter is basically an application of Beer's law. From space, you look down at the Earth and you pick up solar radiation that's been reflected off the Earth's surface, or maybe by aerosols and cloud, and reaches a satellite. And through some fitting algorithm of a backscattered spectrum, you can deduce the amount of methane that was along the optical path. And then you can convert that into a total column of methane. There's two bands that we like to use for this purpose, a band at 1.65 micron and a band at 2.3 micron. You see, the band at 1.65 micron is the advantage of it being co-located with CO2. And that provides a very convenient calibration. And Christian Frankenberg pioneered that technique more than 10 years ago. The band at 2.3 micron is stronger. On the other hand, the solar radiation at that wavelength is weaker. The 2.3 micron band has some other advantages. I guess I don't need to go into this. All the observations that we've had so far of methane from space have been from low elevation orbit. And that includes our current workhorse, which is the GOSAT satellite that was launched by the Japanese Space Agency in 2009. That includes a Skiamachi instrument that operated from 2003 to 2012, and also the Chopomi instrument that's expected for launch in August of this year. And I will tell you a little bit more about those future satellite instruments later on. You see that when you're in low elevation orbit, you observe the whole globe. You basically have an orbiting period of about an hour and a half. From a practical standpoint, in the solar backscatter, you can really only observe over land because the ocean is too dark, doesn't give you enough reflection. An exception, as Chip Miller pointed out to me at the workshop, is in the glint mode when you're looking at the specular reflectance from the sea surface, but that gives fairly sparse sampling. Now, we are very excited in the community that a new instrument called GeoCarb was selected last December by NASA to fly in geostationary orbit and to measure the concentrations of CO2, methane, and CO with the idea of being able to constrain the surface fluxes. So when you're in geostationary orbit, 36,000 kilometers away from the Earth's surface, you have a period of rotation around the Earth in the equatorial plane of 24 hours. So you're always looking at the same spot. And so GeoCarb is designed to look at the Americas, North and South America, and the advantage of being in geostationary orbit, well, you're looking always at the same spot. You can integrate over a very long time. If there are clouds in the way, well, you just wait for the clouds to go away, and then you take your measurement. It's very excited about the opportunity to operate in that orbit. Okay, let me show you the kind of observations that we have right now. So this is the GOSAT satellite data, and this is 4 years of data, 2010 to 2013. And let's first look at this global map here. You see where methane is high is over China, and that's a lot of coal mining, also a lot of rice agriculture. You see very high methane also over India. We think that's mostly livestock, maybe also some landfills. You see wetlands over Central Africa. You see a very interesting hotspot over here that people don't talk too much about. Over coastal Venezuela, that's Lake Maracaibo. That's one of the largest oil fields in the world. Okay, you see all kinds of interesting stuff. But let's take a parochial look of the US. And so what I'm showing you here is a zoom over the US. And the first thing I want to draw your attention to is that even though GOSAT provides you with a global perspective on methane, and in general, you would think satellites would be an ideal vantage point for observing methane because of a global continuous perspective. The observation is actually fairly sparse. GOSAT is designed that it always look at the same spot, so in the places where it observes, it gives you very high quality data, but it only observes about every 260 kilometer along the flight track. So it's not along the orbit track, so it's not a very dense data set. Okay, be that as it may, let's look at some of the interesting features here. Well, what do we see? We see the pig farms in eastern North Carolina. That's pretty cool. We see here some oil and gas and maybe some coal mines in West Virginia. Oh, we're in California here. You see Bakersfield and you see the San Joaquin Valley. So a lot of sources from livestock and oil and gas and the California Air Resources Board, and very interested in figuring them out right now, and I think giving a lot of money to Caltech and JPL to figure this out. You look at what's happening in Oklahoma. This is probably oil and gas, although there's also a lot of livestock there, and you can see a lot of other little features. Okay, now beyond the pretty pictures, how do you do a quantitative interpretation of emissions on the basis of those data? Well, use those inversions that I talked to you about. And what I'm showing you here is work from my, work from my student Alex Turner, who I think gave a talk here. Let me see. Okay, the movie's turning on by itself. This was a 2-year inversion of GOSAT data. So the way we do this, again, we start from a prior emission inventory with pretty high spatial resolution. And then with that inventory, we run our atmospheric transport model. This is what is shown here. Then we confront it to the satellite observations. And then we do some clever fitting, accounting for errors. There's quite a bit of statistical theory involved in that, and in the end we come up with an optimal representation of the methane field, and this gives us correction factors to our prior inventory. Okay, prior inventory being lingo in the inversion world for the bottom-up inventory that we used as an initial guess. So what is it that we find from those correction factors? Well, we find some, again, at the global scale, we find some interesting features. We find that the emissions in China were overestimated. You know, China is always viewed as a bad guy. Well, here they're not as bad as Edgar thought it was. You see that northern Venezuela is much higher than in the Edgar inventory. You see a few other interesting things. But again, let's be parochial and see what's happening over the US. So what I'm showing you here are the correction factors on the scale of the US using a high resolution version of our chemical transport model with boundary conditions that have been provided by the global inversion. And again, the red colors means where the emissions were underestimated, and the blue where the emissions were overestimated. Again, overestimate, underestimate applies to the Edgar inventory and this LPJ wetlands. Okay, well, you see some interesting features. You see that LA was overestimated. But the big thing that catches your eye is this big underestimate over the south central US. And when you see that, you say fracking, 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 fracking. No, well, wait a minute. It's more complicated than that. Because there's a lot of overlap between oil and gas production and livestock activity. And unraveling this is a little tricky. And again, this is a work from Alex Turner, and we spent some time trying to figure out whether we could separate the two, because of course that's $1 million question. Okay, it's fine to say that South Central US is too low, but what is it that's driving that? We couldn't figure it out. And I'll tell you in a minute what we're doing right now to try to solve this problem. But before that, let me, if you just look at the scale of the US, okay, and we care about the national scale because this is what the US has to report to the United Nations. Okay, we have to report to the United Nations Framework Convention on Global Change how much methane we're emitting in individual years. Okay, and what we find in our optimization is that we get a source from the US of about 40 teragrams per year. compares this to the EPA national estimate of 27 teragrams per year. And what we're saying is that EPA, you're way too low in terms of the emissions that you're reporting. We're actually not the only ones to have said that, right? This has been there's been a lot of papers on this about how the EPA emission inventory is too low on the basis of atmospheric inversions. Okay, now, you talk to the EPA folks, they say, well, you know, your atmospheric inversions, you're doing funny things. First of all, you're not actually comparing to our inventory. Okay, you're using EDGAR. Well, what is EDGAR? I don't know. You're not comparing to the EPA inventory. And this is really fair enough. The problem is that we cannot use the EPA inventory as a prior in our analysis because that inventory is not available with high spatial resolution. And that's what we need for inversions, right? In an inversion, we need to have spatial patterns in concentrations that we can compare to observations. From the standpoint of national reporting, EPA doesn't really care where the emissions are within the US. They just want to know the national totals. And that's much easier to get at than trying to get to the highly spatially resolved inventory. So the EPA inventory is exquisitely fine when it comes to processes. And it gives us, for example, a detailed breakdown of the different source components. You see here the natural gas, the waste, and agriculture are the three big ones, but it doesn't give us any spatial information. So my student Bram Massacres, who's here at the workshop, went out to solve this, working in collaboration with EPA. We took the EPA inventory and we distributed it spatially for all of the different little slices of this pie. And this is the outcome. So this is our new spatially resolved version of the EPA methane inventory that we now want to use for inversions, okay? And you see, again, you see the San Joaquin Valley here. You see the Four Corners source that was first identified by Eric Court, which is one of the biggest sources in the US. You see all kinds of interesting things. You see here the back-end oil fields. All right, now let's compare to, by the way, look at the South Central US. You see pretty high emissions in the South Central US. Okay, let's compare this to EDGAR. Okay, here's EDGAR. No comparison. Okay, well, you know, totally different. In particular, in the South Central US, EDGAR is just way lower. All right, the reason for this is that the EDGAR inventory put all the source from oil and gas where people live. All right, this is the reason, by the way, why their estimates of emissions in LA was too high. This is clearly wrong. Now, EDGAR is now producing a brand new inventory, the so-called EDGAR 4.3 inventory. And I'm just showing this for the benefit of the people who are in the workshop. This is a 4.3 inventory. You see it looks totally different from the 4.2 inventory. Problem is that it's just as wrong. You know, what they did in 4.3 is now they took all the oil and gas emissions and put it in the oil fields. Like in the back-end oil field and you know, in Texas, and then they have emissions also from pipelines. But now they have no more emissions from distribution. Very strange, very strange. So I think we're going to be using that EPA inventory in our work ahead. But the interesting thing you see is that the results of the inversion, so the underestimate of the emissions, is very much contingent on the patterns that you assumed as prior. And the fact that EDGAR was so low in the South Central US as a prior means that we could have gotten, and other people could have gotten, the wrong result and have unfairly criticized EPA. So we're now working on trying to do a new inversion with that much improved inventory. And this is work from Bram Massacres. So far, what we have done is the global inversion that provides a first step towards trying to get at US emissions. And this is very preliminary results that Bram Massacres may be vaguely embarrassed by me showing. But what I'm showing you here is our inversion in which we optimize methane emissions globally on a 4 degree by 5 degree grid, so about 500 kilometer resolution, And at the same time, since now we have 6 years of data, we optimize trends. So we optimize linear emission trends over that period, and we also optimize the trend in the global OH radical concentration, which you will recall provides the sink. Okay, let me just focus on what we see about trends here, because I don't want to spend too much time on this. One thing that we see is that a large fraction of a trend is actually driven by a decrease in VOH concentration. And that's consistent with some other work that I'll talk about in just a minute. But we're talking about a 4% decrease in VOH concentration. Why is that? We'll talk about this in just a minute. Let's look at the trends in emissions. What we find is that emissions in the tropics seem to have increased, in particular over India. And this is most likely biogenic methane, whereas emissions at northern latitudes seem to have decreased, and so there's some kind of offsetting effect, and this is most likely fuel methane, so maybe coal mines in China, oil and gas in Europe. Interestingly, this could help to explain the isotopic record. This is something that Uwe Nisbet has been telling us at the workshop, is that the methane has been getting lighter over the past decade, consistent with an increase in biogenic sources or maybe a decrease in fossil fuel sources. And this is kind of consistent with what we're getting from the inversion. Okay, let me talk a little bit about the trend in OH, because most inversions so far have assumed that OH is a constant of nature, that OH never changes. And so the only lever that you have for changing methane concentration is to go after methane emissions. But clearly, that's really not true. And I don't want to spend too much time on this, because I think that Alex Turner visited here a few months ago and gave a seminar on this. Did he?
Yeah, but this might be a bigger audience.
It's just because it's your work, Christian. Anyway, Alex is a really sharp student, and like me, he loves hanging around at Caltech. So he's been spending quite a bit of time here working with Christian and also with Paul Wenberg. And this is a result from a two-box inversion. So Northern Hemisphere and Southern Hemisphere from 1982 to present. So using a box model just to be able to make the computation tractable. And inverting together the methane concentration in each hemisphere, the delta 13 of methane, and then the methyl chloroform concentration, which provides a proxy for a global OH. And I don't want to spend too much time on that. But what we find from this analysis, and this was a paper that led by Alex and was co-authored by Christian, Paul, and myself, is that the most likely solution for the trend in methane, and in particular for what's happened over the past decade, is a decline in OH. So over the past decade, what we explain the trend best by a decline in VOH concentrations. And interestingly, we find that this is consistent to some degree with constraint from observations of methyl chloroform and other halocarbons that were published by Steve Munska of NOAA a few years ago. Now, we can't be too brash about this, because in fact, in this analysis, we just use surface observations, and surface observations are not enough to really constrain the drivers for the trend. And in fact, what we find in the inversion is that we can get an almost as good solution from a cost function point of view by having fixed OH concentrations and just an increase in methane emissions. But what we showed in this paper is that you cannot discount the possibility of changing OH concentrations as an explanation for the renewed growth of methane over the past decade. So why is it that OH concentrations would change? So what I'm showing you here in the top is a textbook diagram of what controls OH concentration, and involves radical cycles. OH is produced by the photolysis of ozone and the presence of water, and its concentration is controlled by the cycling between NOx radicals, and the sink is by oxidation of CO, as well as by methane and other volatile organic compounds. When you run this complicated soup in a 3D model, what you find is that the results from the model can be parameterized pretty well in terms of this simple equation in which the global mean concentration of OH is proportional to the photolysis frequency of ozone, to the NOx emission, and inversely proportional to the emission of CO and volatile organic compounds. The important point I want to make here is that all of these terms on the right-hand side are subject to change. And in fact, we know that the emissions have changed tremendously over the past century and keep on changing on a timescale of decades. Granted, not so much on a year-to-year basis. But on a year-to-year basis, the photolysis frequency could change quite a bit. Fluctuations of ozone in the stratosphere, changes in cloud cover. The amount of water could change. And then, of course, natural sources, such as lightning, could also change quite a bit from year to year. So on the bottom panel here is a paper by my former student, Chris Holmes, who worked with Michael Preter. He's now a professor at Florida State University, showing the interannual variability of OH concentrations between 1998 and 2010 from observations, again, from the proxies I was talking to you about, and then from various models. And the important point I want to make is that OH varies by about 5% on an interannual and decadal basis. So when you are looking at a trend in methane of a few percent, hey, you could easily explain that on the basis of OH. Okay, let me now turn my attention to the future. So we're really at the dawn of the era of satellite observations of methane. So we've had Ski-Hamachi, it's now rest in peace. We have GOSAT, that's alive and kicking. And then we have several other satellite instruments that are waiting at the gate. And I want to tell you about 3 of them. The first one is CHOPOMI, that's going to be launched by the Dutch in August of this year. And that's going to provide global daily coverage with 7 by 7 kilometer square pixels. Okay, so whereas GOSAT was really half blind, just observing one spot every 260 kilometers, CHOPOMI gives you blanket coverage. Another one I want to tell you is this geostationary geocarb instrument. 3 by 3 kilometer square pixel observation 2 to 3 times per day. And then I want to spend also some time telling you about an instrument that actually was launched in June of last year, but is just now starting to provide observations. That's GHGSat. And that's a whole new observing concept. This is from a Canadian company called GHGSat Inc. And what they're doing is, instead of trying to observe methane all around the world, they're just observing selected scenes, 12 by 12 kilometers square, and observing those scenes with very high pixel resolution to be able to observe methane at the facility level, at the level of point sources. And here, the idea is that they will get paying customers wanting to determine how much methane is coming from their facility, and so paying for some observations and so on. That's a business model, and I have a graduate student, Daniel Warren, who has been working with them for the past year. Okay, let me tell you a little bit about the potential of those future observations. What I'm going to show you here is a little movie of observations for 2 days over the Barnett Shale. And it's just very conceptual, but it's going to compare GOSAT, CHOPOMI, and geocarb over a particularly interesting region in northeast Texas, the biggest oil gas field in the contiguous US, but also with a lot of livestock sources, and of course, the Dallas-Fort Worth urban area. So we're going to first see what we can get from GOSAT in terms of observing that scene for 2 days. This is January 3rd. We're not seeing anything. Okay, so much for that. January 4th. Oh, we have one observation here. Okay, so we had one observation over that whole domain in 2 days. Now let's see what we're going to get from CHOPOMI. So CHOPOMI has observed, global daily, so once a day, 1:30 p.m. So, whoa, this is GOSAT on steroids. I mean, And then the next day, unfortunately, clouds are coming in the way. And so as a result, you can't see too much. Okay, well, let's see what we can get from geocarbs, from geostationary orbit, where we're going to be observing twice per day, and with 3 by 3 kilometer square pixels. So let's look at, whoa, look at this. And we can hope that information in the early 2020s. The beautiful thing also about geostationary orbit is that you're not as affected by clouds. See, the second day, it's cloudy, but you're observing before the clouds roll in. And so, all right. I want to finish this talk by telling you about the challenge of observing point sources at the facility level. And this is something for which there's considerable interest. I actually spent some time on the phone talking with BP about this just last week. They wanted to figure out what we could do. And this is something where Christian, again, has been doing some really pioneering work. This is his paper over the four corners, doing airborne remote sensing of methane point sources in a region where methane emissions are some of the highest in the United States. And what you see is that there's a fundamental challenge in observing methane point sources. They are many and small and variable. There's no whooping big source of methane, well, except Aliso Canyon. All right, fine. But most sources are just little leaks. And but you want to be able to quantify them. And even the so-called super emitters, well, they're bigger leaks, but they're not that big. Okay, so we have a problem of scale. Let's consider, for example, our ability to observe one of the largest point sources observed by Christian at Four Corners. This one here, 1.6 tons per hour. That's a pretty whooping big source. And let's see whether we can observe this with GoSat. Well, with GoSat, we just smeared over the whole pixel. We can't see anything. All right, try Chopomi. Dead. Okay, no, it's not working. All right, so this is where the GHG-SAT concept really is very important, because the whole idea is that by using very fine pixels, you avoid the dilution of a small point source plume over an excessively large area. And so with an instrument like GHG-SAT, you would actually be able to resolve that plume seen by Christian. Okay, I'm kind of running out of time, so what I want to do is leave you with the very first observation that we have from GHG-SAT. And I say it's the very first observation, made it public just yesterday. And this is the methane plume from the Lampangar Dam in eastern Cameroon. So that's right here. You might say, why has GHG-SAT been observing dams? We're very interested in hydroelectric reservoirs as a source of methane. When you have flooding of a hydroelectric reservoir in order to generate electricity, what you're doing is you're submerging a lot of organic matter that is now going to produce methane under anaerobic conditions. This is, we think, one of the big unrecognized sources of methane, and one that we wanted to quantify. Now you might look at this and say, reservoir, where's a reservoir? This is actually something I picked up from Google Earth this morning. And the image is actually from 2014. This here is a spot image from 2016. So Lampangar is a brand new dam. And it was built by the French EDF. Look at all this vegetation is now underwater, ready to make methane like gangbusters. And this is what we see. This is what we see. This is the plume of methane that we see from GHG-SAT. And we've seen it twice over the same spot, so we have some confidence that it's real. On the basis of the size of the plume and using techniques that Christian taught us how to do, we can make a first estimate of the magnitude of that source, and we get a value of 8 tons per hour. That's a whopping big source. It's not a crazy source. the biggest coal mine vents in the US are of that magnitude, but it's a whopping big source. And you might wonder, why is it that we're seeing the emission right at the dam? The reason for this is because the turbines are just processing the water as it flows under the dam, and they aerate the water, and the methane just goes off. So in other words, you're not seeing the methane bubbling all the way throughout the reservoir. There's probably some of that, but where you expect to get the largest methane source is right at the dam where the aeration is taking place in a forcible manner. And with this, I want to thank you very much for your attention. Great pleasure to be here. Thank you.